Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about solutions to the Schrodinger equation, and specifically I'm going to be talking about the quantum numbers. And so when we talk about solutions to the Schrodinger equation, we're talking about wave functions. And so the wave functions themselves are the solutions, and there are many solutions to the wave equation. And the wave solution, or the wave function, I should say, is a very complicated mathematical equation itself, or a function. And so I'm not gonna get into that, except just to say that out of these wave functions fall out these numbers called quantum numbers. And so these quantum numbers have some meaning when it's with regard to the electrons in the atom, as well as the orbital of the atom. And what we said before with regard to the orbital is that the orbital is just a mathematical probability map of where you're going to most likely find the electron in a region or space around the nucleus of the atom. And so the quantum numbers will describe that orbital as well as the electron. So three of the quantum numbers are describing the orbital itself, that probability map of where the electron is most likely to be 99% or 90% of the time. And then a fourth quantum number is going to describe the electron itself. And so the four quantum numbers are the n, which is your principal quantum number. And your principal quantum number says something about the energy and overall size of the orbital. So this has to do with energy and size of the orbital. So that's the first one. So that's your principal energy level, and it's represented by the letter N. The next quantum number is L, and this is referred to as the how do you say, not the magnetic quantum number, but it's referred to as the angular momentum quantum number. Quantum number. And the angular momentum quantum number kind of indicates the shape of the orbital. So we have the overall size and energy of the orbital, and then we have this quantum number indicating the shape. So this has to do with the shape of the orbital. And then the third one is going to be M sub L, and this is referred to as the magnetic quantum number. And this one has to do with the orientation of the orbital itself. So the orientation of the orbital. So orientation of orbital. This one has to do with the shape of the orbital. And I'll talk about these more in a bit. So these three quantum numbers give you these three are going to be talking about the orbital itself. So energy and size of the orbital, shape of the orbital, and orientation of the orbital in space. And then we have finally the fourth one is m sub s, which is going to be the spin quantum number. And this has to be the spin. It refers to the spin of the electron itself. So the spin of the electron itself is represented by this number. And all four of these are related to each other, okay? Especially these three. These three are going to be related to each other. So you can relate them through mathematical expressions. And so here, each of these has a number associated, or a range of numbers associated with them. And those numbers mean something according to these indications here. So n can have any integer 0 or greater. So n can be 1, well, it can't be 0, but it could be 1 or greater. 0 is not an option. So it could be 1, 2, 3, 4, and so on, up to infinity, right? So can we have any integer, 1 up onto infinity? Okay, so this has to do with energy. So the higher the number, the higher the energy. And as we saw before, this has to do with the Bohr model. So here's your nucleus. Here's one shell or orbit. Here's another shell or orbit. And here's another shell, and so on. And each shell, as you get starting from the inside out, the closest orbit is number 1, n equals 1. The next one is n equals 2. The next one is n equals 3. And so the farther away you get out, away from the center of the atom, the higher the energy. So the energy increases. So number 1 is the lowest energy shell, or energy level. Okay, so the next one, your angular momentum quantum number, L, those have values. So L is going to be related to N. So I can determine what the L values are. So the L values are going to be numbers of, we're going to start at 0, and we're going to go all the way to any integer up to n minus 1. Okay, so n minus 1, sorry about that. So L equals, can have any integer from 0 all the way up to n minus 1. So n minus 1 is the last possible L value you can have. So the L values are limited by your principal quantum number. So you can have limited up to n minus 1. So if you have, if you're at energy level number 2, then the largest L value you can have is 2 minus 1, which is 1. And I'll show examples of this in a moment. Your m sub L values are related to your L values, your angular momentum quantum number. So in this way. So your m sub L values can have values from -1, or from negative L to 0, all the way to positive L. So again, your L values limit the range of your m sub L values, your magnetic quantum number. Okay. And the value of your m sub s, your spin, can only have 2 values. It either spin up, which is represented by plus 1/2. So that's the value of spin up. Or it can be spin down, which is equal to negative 1/2. So you're either positive 1/2 or negative 1/2. So you only have two possible spins. You're either spin up or spin down. And so that's going to be so these are how you relate the numbers together. So these are the values and the range values you can get for each of the numbers. So let me do an example to explain this. Okay, so let me go over and show you how these are all related to each other by several examples. So let's start with n equals 1. So let's say we're at quantum level or principal energy level number 1. Okay, now if we're at energy level number 1, that's number 1. The 1 is the number given to your n value. So then what are the L values that come from that, your angular momentum quantum numbers? Well, if you've got n equals 1, then your L values are going to be integers from 0 to n minus 1, right? So if we we'll start to 0. So in this case, for n equals 1, your L values at this energy level are going to be 0 and then all the way up to n minus 1. But what is n minus 1 if your n value is 1? So 1 minus 1 is 0, so 0. So 0 is the only L value, right? And we give a special letter to this number 0 for this quantum number L, right? For 0, you would say that is your S. That's given the letter S, okay? So this is where we get what is called the S orbital, okay? And then you can get your M sub L values, M sub L values from that as well. So your magnetic quantum numbers come from the L. Well, remember, your M sub L values range from negative L to positive L, but in this case, your L value is 0. So there's negative 0 and positive 0 is just 0, so you only get one value called 0. And so in this case, at principal quantum number 1, you only get one number for your L value, 0, which is labeled S. And then from your L value, you only get one number for your M sub L value. And so in this case, your S orbital, remember your L values refer to the shape of your orbital. Well, the shape of this orbital, the S orbital, is spherical, right? So it's a perfect sphere, right? Three-dimensional, looks the same all around. So if your M sub L value refers to the orientation in space, well, how many ways can you orient a sphere in space that it looks different? None, right? No matter how you turn it, the sphere looks always the same. So you only get one value because there's really only one orientation of a space, of a sphere, and that's any one. So it always looks the same. So there's really no one number for your M sub L value. Okay, so and then the spin just is determined by the electron, and the electron's spin is always going to be plus or minus 1/2. So it doesn't matter what these numbers are; it's always going to be plus or minus 1/2. Okay. In the next part, I will continue with this.